All right, the last thing we need to address in this course is moment of inertia. Okay, moment of inertia is something you've probably encountered in the past. It deals with the resistance to rotating motion. I talk about an object here, say I've got some sort of object, and it's, imagine this three-dimensional blob rotating about this axis. Okay, somewhere in here, there's this little differential element, dm, and its distance r from the center. Okay, the moment of inertia, it's just also technically known as the second moment of the mass of the element. Okay, essentially it's the mass times this distance squared from the axis. Again, it's a complicated definition. It's in your textbook if you want a more thorough explanation. But really what you need to know is the resistance to motion, this moment of inertia term, is dependent on the mass of the element times the distance from the axis of rotation squared. Okay? So if I look at a more simple two-dimensional example, okay, if I look at, say, x and y, I have my big blob here, and I have some differential element in the middle. Okay, I'm going to have some distance y from the x-axis, some distance x from the y-axis. Okay, well, the moment of inertia rotating about the y-axis is equal to the integral of x squared dm. Okay, but again, we're going to be dealing with things that tend to be uniform in density. So again, we're just going to do this times the area of that element. Okay, the moment of inertia about the x-axis is going to be the integral of y squared dA. So again, it's the area of the element times the distance from the x-axis, the distance here is y, for a moment of inertia about the x-axis. Moment of inertia about the y-axis is about there. This is, again, the resistance to rotating about the y-axis, rotating about the x-axis. Okay. Now, we can also talk about this distance here. This actually gets, this is the origin, a different symbol, j. Okay. This is called, I is the moment of inertia. J is called the polar moment of inertia. Again, because we're talking about things more or less in terms of polar coordinates here, in terms of radius instead of x and y coordinates. That's the integral from, that's the integral of r squared dA. Now, because x squared plus y squared equals r squared by the Pythagorean theorem, j about the origin, again the polar moment of inertia about the origin, is equal to ix plus iy. Because x squared plus y squared equals r squared, we can substitute these in, and we do get that term there. Another way to think about this is rotating about the origin. Now we're talking about this thing rotating this way, which, if this were a three-dimensional problem, we'd be talking about rotation about the z-axis. Okay? When we talk about two dimensions, it becomes the polar moment of inertia as it rotates this way. If we were a three-dimensional problem, we'd really just call this iz. But that gets a little bit more complicated. Three-dimensional moments of inertia, we start dealing with the ability to rotate around multiple axes at once, which is beyond the scope of this course. So for what we're doing here, it's going to be moment about the y, moment of the x, and then the polar moment, which is moment about the origin. Okay, starting with a quick example here of calculating moment of inertia for a relatively simple object here. If I have a sort of wedge-shaped object here, and this curve will follow the pattern y equals x cubed. This will go from 0 to 2 in the x, and this will go from 0 to 8 in the y. Clearly not to scale, but close enough for what we're doing. Okay, ultimately we want to, and I'm asking for find moment of inertia about the x-axis. All right, well, for moment of inertia about the x-axis, we end up with ix equals the integral of y squared dA. Now, we can't just immediately integrate that because we have this dA term that we need to deal with. Now, when you think back to centroids last week, we had the choice anytime of choosing a vertical rectangle. This distance here would be 8 minus y. And this distance would be dx, and we'd have dA equals 8 minus y times dx. Or we could do a horizontal rectangle, in this case with x and height dy, giving us dA is x dy. All right, and in this case we'd integrate over x, and in this case we'd integrate over y. Now, in centroid, you can choose either of these methods. When we're doing moment of inertia, we care about how far things are away from the x-axis. We care about this y distance here. We cannot integrate over x. Okay? When we're looking for distance from the y, we're calculating a moment of inertia about the x-axis. We have to calculate distance away from the x-axis and integrate over that distance. So we have to integrate over y. Okay, it looks like you should probably get the same answer if you do it either way. It ends up not being true because of this y squared and the definition of moment of inertia here. You do need to integrate over y. So that means our dA just became x dy. So ix equals the integral of y squared x dy. All right, we're integrating over y, so we're going from 0 to 8. All right, we need to substitute in for x. X is simply y to the 1/3. So ix equals the integral of 0 to 8 of y squared times y to the 1/3 dy, which obviously equals 0 to 8 times y to the 2 1/3 dy. Integrate that. Ix equals 1 over 3 1/3 times y raised to the 3 1/3, evaluated from 0 to 8. Okay, do that out, you end up with an answer of 307.2, I believe. 307.2, and the units here, again, y squared times area, meters, meters, meters squared. I didn't label these, we'll call them meters for the sake of simplicity. This is meters to the 4th. Okay, simple example here of using this integral to do the to find the moment of inertia about the x-axis. If we wanted to find moment of inertia about the y, it would be y equals x squared dA, and we would use this vertical and integrate over x, the vertical rectangles, and integrate over x. Okay, so that's a simple case here. Finding moment about the x or y axis, or about the origin there with our polar moment of inertia. Now, it oftentimes comes to be that we're not looking for moment of inertia about one of our axes. We're looking for moment of inertia someplace else. There is a way to deal with that. And that is called the parallel axis theorem. Okay, the parallel axis theorem, if we have, okay, say we have a circular object, we know its moment of inertia right through the middle. So this will be y, we know iy. Now, what happens if we want to move the moment if we want to find the moment of inertia about one of its edges? Okay. Well, the parallel axis theorem gives us an adjustment term to compensate for the fact that we're not taking moment of inertia about the center. Okay. So this is I x equals I'll explain what these are in a moment. These are subscripts, not differentials. And then J O. Okay. All right, what these are, Ix bar, Iy bar, and Jc bar, these are moments of inertia about the centroid of an object. And these other terms, dy is the y distance from centroid to the new axis of rotation. Dx is the x distance from the centroid to the new axis of rotation. And d is simply the true distance from the centroid the new point of rotation. Because keep in mind, when we're rotating, when we're talking about polar moment of inertia, we're talking about rotating about the origin, rotating about a point. If we move that point over to some other place and cause rotation there, it's just the true distance that we've moved. Okay? This may seem not all that useful. It's like, oh, I have to find the moment about the centroid, the moment of inertia about the centroid before I can even use this. Okay, A is area in all cases. But what makes this incredibly useful is reference tables. Okay, on the back cover of your textbook are moments of inertia about the centroid of many, many common shapes. So that example I gave a moment ago, okay, I have a circle, say it's got radius 5 inches. Okay, I can actually look up. So this is my original y-axis. This is what I'll call my y prime axis here. Okay, my original y-axis, so Iy through the centroid, I can simply go to the back of the textbook. Right there, fourth one down, moment of inertia about the y-axis for a circular area is given as 1/4 pi r to the 4th. Okay, well, now I can simply use the parallel axis theorem. If I want to find out what this one is, I have my new Iy here, equals Iy for the centroid is 1/4 pi r to the 4th plus a dx squared. Well, the area is pi r squared, area for the circle. Okay, dx is the x distance from the centroid to the new so that's this distance here. That's simply 5. I'll sub in 5 for my radius as well. Okay, so this 5 for my radius here as well. I can solve this very quickly here. 5 to the 4th times pi divided by 4. So the moment of inertia about the centroid is 490.87 plus 5 squared is 25 times 5 is 125 times pi is 392.7. Total inertia here, total moment of inertia about the endpoint. Okay, notice that, again, moment of inertia about the centroid is going to be less than any other value. This ends up being 883.57. And I did that in inches, so this is inches to the 4th. Okay, very simple. Again, generally, if we have some odd-shaped object, something of that nature, you're going to end up having to use the integral. But if we have a regularly shaped object, it's oftentimes easier to look up the moment of inertia about the centroid and then just shift it to where your new axis of rotation is, rather than setting up a new coordinate system and trying to integrate over a circle, which is an unpleasant piece of math to do. Okay, we can just look up moment of inertia about the circle about its center and then shift it wherever we need it. Okay, if it's not something that's on the reference tables, then generally the parallel axis theorem is just an extra step on top of finding the moment of inertia. But if it's something where we can look up a nice regular shape and just shift the axis around, again, parallel axis theorem makes our life a lot easier. Okay, the last thing we need to talk about is the same thing as we wrapped up last week, and that is composite bodies. Okay, this is very simple, very similar to what we did with centroid. In fact, it's even easier, okay, because we can just find, we don't have to do any sort of weird particle addition at the end. It's literally just adding up the moment of inertias of each of the individual pieces. So if I were to take a relatively straightforward example here, if I have x and y axes, which should be straight in theory, and I have a shape that looks like this, and there is a hole missing, so our object looks like this. All right, dimensions, we're going to go 15 centimeters here, 15 centimeters here. The height, 100 to, oops, 10 centimeters, sorry. 10 centimeters here. And then for the triangle, we're going to give this is 20 centimeters, and the radius is 5 centimeters. Okay, so what we need to do is find the moment of inertia for each of these, for this object. So we'll find moment of inertia for the sake of keeping things easy about the x-axis. Okay, so we're going to rotate it this way. Could be just as easy to do moment of inertia about the y. It doesn't matter either way, the process is the same. So I'm going to split this into 3 pieces. Again, parallel axis theorem is going to make our lives easier. Again, this is a tough thing to integrate. We'd have piecewise defined function here. We'd have a circle we'd have to remove. If I split this into 3 pieces, I'm going to have the triangle, which I'm going to call piece 1, the giant rectangle, which I'll call piece 2, and the circle, which I'll subtract from the end, is going to be piece 3. So I need to find the moment of inertia for each of the pieces. Okay, so this is a triangle, all right? About its centroid is right about here. So its centroid is, I'll do this in a different color so you can see it a little better. The centroid of this triangle is going to be, well, these are all regular shapes, so it does make sense to use the parallel axis theorem. So I'm going to find the moment of the centroid for each of these three pieces. So the centroid here is 20. We need 2/3 of that is, what is that? 20 thirds is 16.67? No, wrong. Why can't I do math anymore? 20 by 3 is 13.33. Sorry, I can't do math at this point. 13.33, and then the y direction is going to be 6.6. Oops. Yeah, 6.67. The centroid here is going to be 20, 35, comma 10, and that's for both directions. Okay. For both, not for both directions, but for both the big rectangle and the circle that we've removed from the middle. Both have centroids at the same spot. So we're going to have to shift things around a little bit, okay, for the moment of inertia of the triangle. Moment of inertia for the triangle. Ix equals Ix bar plus a dy squared. Well, that's equal. Ix bar we can look up for a rectangular area here. Ix is 136 bh cubed plus the area is 1/2 base times height times dy. Okay, our height change in the y here is 6.67 squared. Okay, because we're moving from the centroid, which is at 6.67, down to the x-axis where we'd like to take our moment of inertia. Again, Ix bar gives us the moment of inertia about the centroid. Again, about an x-axis parallel to the centroid. We need to move that down 6.67, so we end up with that term there. This, and I'll spare you some of the algebra here. 1/36 times base is 20 times the height of the triangle is 20 to the third plus 0.5 times the base is 20 times the height is 20 times 6.6 squared is 13,333.3. Centimeters to the fourth. Okay, very big number, but that's not surprising given some of the pieces we have here. Okay, again, the area here is 200 centimeters, so we end up with some large distances. 2, if it makes you feel better, we can convert this to meters, divide by 100 4 times, and that'll get us a much more reasonable number in terms of order of magnitude, but we'll leave it in centimeters for now. 2 is going to be this entire rectangle. Okay, again, we have the moment of inertia. Ix is equal to Ix bar plus a dy squared. In this case, we have Ix bar for the moment of inertia through the centroid. For a rectangular solid is 1/12 bh cubed. Okay, again, the base here is 30 and the height is going to be 20. Plus, again, the area is base times height for a rectangle, times how far do we have to shift it? We have to shift it down. Again, we want a moment about the x. We have it, the moment, 10 centimeters above the x through the centroid. So we're going to go 10 squared. So this ends up equaling 1/12 times the base is 30 times the height is 20, and that gets raised to the third power, plus base is 30 times 20 times 10 this is 80,000. Centimeters to the fourth. And then lastly, Ix equals Ix bar plus a dy squared for the circle. Okay, so again, looking at moment of inertia about for a circle, about its centroid is 1/4 pi r to the fourth. Okay, notice all these equations end up with length to the fourth as their area. Length times length cubed, length times length cubed, or length to the fourth, plus area is pi r squared times dy squared. Again, we're moving it down 10. This is 10 squared. This term ends up equaling 8,345 centimeters to the fourth. But keep in mind that this is the piece that we've removed, so it gets a negative. Okay, so removing that much inertia from the remainder of the object. Okay, if this hole weren't in this piece, it would just be the 13,000 plus the 83,000 would be 93,800. We do have to subtract this 8,345. Add these three together. 13,333 plus 80,000 minus 8,345. We end up with 84,988 centimeters to the fourth. Okay, kind of a big mess there in terms of the number, but the process is really quite simple. You find the moment of inertia of each of your pieces about the axis that you care about. Okay, notice I had to move these around from the centroid to where they were going, to where the x-axis where it's actually rotating about, adding these together. If I were to find moment about the y-axis, okay, I'd have to move this one over 13.33 to get to the y. These two I'd have to move over 35 to get back to the y-axis. So these would all stay the same. Okay, the only thing that would change would be the distances. Okay, and that wraps up chapter 10.